Hello everyone, I'm Ava.
And I'm Jordan.
Welcome to our video. Thanks for stopping by.
Today, we will be discussing optimization. The Oxford Dictionary defines optimization as the action of making the best or most effective use of a situation or resource.
In mathematical terms, that means finding the optimal value or number.
Let's start by looking at the strategy you should use when approaching these problems.
Begin by drawing a picture or diagram that best represents the problem you are solving.
Next, write an equation relating to the problem and the picture.
Then, take the derivative of the equation and set it equal to 0.
Lastly, plug that value into the original equation and solve for the desired value.
Let's start with the first example problem. The question asks, find two numbers whose sum is 26 and whose product is a maximum. We can begin by following this strategy. The first step is to draw a picture. Since there is no picture that can be drawn from the question, we can skip this step. The next step is to create the equation. Since the question asks for two numbers, let's assign variables to these numbers. We can use x and y. Now we create an equation with x and y. Since we know the sum is equal to 26 because that is what the problem tells us, we know that the equation is x plus y equals 26. Now let's set the equation in terms of one variable. We can subtract x on both sides of the x plus y equals 26 equation and make it into y equals 26 minus x. This is where we bring in another equation. This equation solves for the product. It is equal to product equals x times y, or p equals xy. Since we know that y equals 26 minus x, we can plug it into the y in this equation. Our new equation is p equals x parentheses 26 minus x parentheses. We can simplify it to p equals 26x minus x squared. This is where we move on to the third step. We must take the derivative of the product. By following the rules of derivatives, we can determine that p prime is equal to 26 minus 2x. Now we set it equal to 0 and solve for x. By doing this, we get x equals 13. That is the first number. To find the second number, we plug x into y equals 26 minus x. By doing this, we get y equals 26 minus 13. Then we get y equals 13. That is the second number. Now we have our answers, 13 and 13. Next problem.
Let's take a look at problem 2. A rectangle is to be inscribed under one arch of the sine curve. What is the largest area that the rectangle can have, and what dimensions with that area? In this example, we are inscribing a rectangle under an arch of the sine curve. The problem is asking for the largest possible area of the rectangle. Let's start by reviewing our strategy. According to our strategy, we should draw a diagram of the problem. First, we'll draw one arch of the sine curve. The graph of sine looks like this. In the problem, there's a rectangle inscribed under this arch, which would look something like this. Now that we've drawn a picture, we'll refer to our second step, which tells us to write an equation. In this problem, we are looking for the area of the rectangle, which can be represented by a of x equals length times width. On our diagram, we'll call this length and this width. As you can see, there are two segments on the x-axis that the rectangle does not cover. We will assign these segments the value of x. Therefore, length is equal to pi minus 2x because length is equal to the total length of the x-axis, pi, minus the two segments not covered by the rectangle. Now that we have an equation for length, we need one for width as well. In this example, width is equal to sine x because the width of the rectangle is limited by the equation of the arch that it is inscribed in. Let's plug our equations for length and width into our equation for the area of the rectangle. So a of x equals the length, or pi minus 2, times the width, or sine of x. Step 3 is to take the derivative of this equation and set it equal to 0. So let's take the derivative of a of x. Because this equation deals with multiplication, we need to use power rule. As a reminder, power rule is the derivative of the first multiplied by the second, plus the derivative of the second multiplied by the first. So a prime of x is equal to the derivative of pi minus 2x, which is negative 2, times sine of x, plus pi minus 2x times the derivative of sine of x, which is cosine of x. Now let's simplify these values using FOIL. So the derivative of a of x is negative 2 sine x plus pi cosine x minus 2x cosine x. Next, we have to set this derivative to 0 and solve for x. It is not possible to solve this algebraically, so instead we must solve it graphically. We can use the graph of a and find the maximum value, or we can use the graph of the derivative of a, find where a prime is equal to 0, then evaluate a at that value of x. Let's try this both ways to ensure we are getting the correct answer. As you can see, the graph of a has a maximum value of 0.71. Similarly, the graph of a prime has an x-intercept of 0.71. Because they are the same, we can confidently say that 0.71 is the solution to a prime of x equals 0. The fourth step of our strategy tells us to plug this value into the original equation. Let's start by plugging 0.71 into the length. The length at x equals 0.71 is 1.72 units. Now let's evaluate the width at 0.71, and we get 0.65 units. By multiplying the length and width values together, we will get our maximum area, which is 1.12 units squared. Next problem.
Now for the third problem. It asks, a farmer has 100 feet of fencing. He wants to build a rectangular enclosure for his cows. What dimensions gives his enclosure the maximum area? Okay, now we can begin by drawing the enclosure for the cows. Since we don't know the dimensions of the enclosure, we can just make a rough sketch of it. Now it's time to create the equations. Let's start with what we know. Area is equal to width times length, and perimeter is equal to 2 width plus 2 length. We can use x and y to represent width and length. We know what the perimeter is going to be because the problem told us that. We can plug in the 100 feet into the perimeter equation to make 100 equals 2x plus 2y. Now we can simplify the perimeter equation because everything can be divided by 2. The new equation looks like this. Let's isolate the variables now. We can substitute x on both sides to make y equals 50 minus x. Now we can plug in 50 minus x into the area equation. Since 50 minus x is equal to y and 50 minus x is being plugged in, the new equation should look like this. The next step is to take the derivative and set equal to 0. So let's do that real quick. By setting it equal to 0, we get x equals 25. Now let's solve for y. We can do that by plugging it in the old perimeter equation. Y is equal to 25. We are now done with the problem. Our dimensions are 25 and 25 for the enclosure.
Let's take a look at this next problem. A police officer has to cover a crime scene with an area of 800 feet squared. She is enclosing the rectangular crime scene along a river. She does not need tape for the river itself. What are the dimensions that require the least amount of tape? In this problem, we are looking for the smallest possible perimeter needed to cover the given area. Because the crime scene is along a river, we do not need to include that in the perimeter. As always, we'll begin by drawing a picture. The crime scene is rectangular and is bounded on one side by a river, like so. We are given the area of the crime scene, 800 feet squared, and are asked to calculate the dimensions of the rectangle. Let's label this L for length and this W for width. Following our strategy, we know our next step is to write an equation. We are looking for the minimum perimeter of the rectangle. Our equation for the perimeter will be P equals L plus 2W because the tape is covering both sides of the crime scene but only one length, as we do not need tape to cover the river. We also know that 800 equals length times width. Let's take our equation for area and isolate one variable so we can substitute it into our perimeter equation. Let's divide this equation by width to isolate length. Now we have length equals 800 divided by width. When we plug this value into the perimeter equation, we get P equals 800 divided by width plus 2W. Now we can take the derivative and set it equal to 0. By taking the derivative, we get negative 800 divided by W squared plus 2. Let's set this equal to 0 and solve for width. We'll start by subtracting 2. We need to get W squared out of the denominator, so let's multiply both sides by width squared. Now, negative 800 equals negative 2 width squared. We'll divide both sides by negative 2 to isolate the width. Next, we'll square root both sides. The square root of 400 is 20, so width equals 20. Now we can plug this value into our area equation to find the length, so 800 equals 20L. When we divide both sides by 20, we get length equals 40. Now we have the dimensions of the rectangle. Let's look at one final example problem.
This is our last example problem. It asks an open top box is to be made by cutting congruent squares on the side length x from the corners of a 20 by 25 inch sheet of gold and bending up the sides. How large should the squares be to make the box hold as much as possible? What is the resulting maximum volume? Let's draw what the box is going to look like. We are also going to draw the base of the box so the squares are being cut into the base to make the box. Now the equation. The equation for volume is length times width times height. We can give height the value x. To find the values for length and width, we have to do a little bit of thinking. First, we can put length as equal to 20 inches and width equal to 25 inches for the sheet before it is turned into a box. We can refer to the drawing of the base to make this easier. Now we can cut the squares into the corners of the box. Since the height of the box is the size of one side of the square, we can label them all x. As the drawing now shows, length, which was 20 inches, is now 20 inches minus 2x for the volume. 2x because we have to account for both ends of the length. This same thinking makes width equal to 25 minus 2x. Now we have values for height, width, and length. We can now plug these values into the volume equation, which should be volume equals x parentheses 25 minus 2x parentheses 20 minus 2x parentheses. Let's simplify it to make 4x cubed minus 90x squared plus 500x. Now we take the derivative and set it equal to 0. We can use the quadratic formula to solve for the value of x. The two values we get are 11.32 and 3.68. To find out which one is correct, we can plug them back into the volume equation. By doing this, we get negative 70 for the 11.32 value. This is the incorrect value, considering that volume cannot be a negative number. We plug in 3.68, we get 820. This is our correct answer. 820 is the maximum volume. The other part of the problem was to see what the size of the sides should be. Since the side of the square is height and height is equal to x, we know that the side of the square should be 3.68. We are all finished. Now let's see how optimization can be used in the real world.
Optimization can be used in the real world in many different ways. For instance, building a fence around a yard to contain a dog. Using optimization, you can find the most efficient way to build this fence while maximizing area but minimizing cost. Look at this happy puppy.
Another instance includes applying carpeting to a classroom. Through optimization, you can find the best way to install your carpet in the classroom. Optimization is a powerful and fun tool used by engineers all the time.
No.
Look at that happy teacher! As you can see, there are many different ways optimization can be used in the real world. By using your strategies, no optimization task is too difficult.
Thank you guys so much for watching. I had a blast. This is Jordan signing off.
Goodbye everyone, this is Ava signing off.